So this is an Ethereum slot today, right? So Justin kind of set the stage for this already. You have 12 seconds in a slot. At the second 0, the proposer released the block and the payload today, right? This is based on the specification, the honest validator behavior. And then 4 seconds into the slot, the attester votes on what is the canonical view of the chain, right? So it releases votes. And then 8 seconds into the slot, the aggregator will aggregate those votes and then submit their vote, right? So the reason you have this aggregator is that we have 1 million validators today. That's about 30,000 validators will vote once per slot. And that is just a lot of signatures for any solo validator to verify, right? So you have this like honest duty of aggregator helping to aggregate the votes such that it's cheaper for no more validator stakers to validate, right? And then 12 seconds in, proposer release, the net slot proposer release their block, their payload, and also the aggregated votes of the previous slot, right? And those gets paid, so people will do those honestly, we assume. And then what is important here is that the votes determine the head of the chain, okay? And then the votes could come from 2 different places, P2P or in the block, right? And then only the finality that we love, we care about is coming from the block, but everything else can come from the P2P and the block, right? So what is the assumption here? The assumption here is that the block should take 1 second to arrive, then the attester could have 3 seconds to verify the block, and then the net slot proposer have 11 seconds to build a block, right? I mean, isn't life so simple if we just view it like that? And then if you see the chart here, basically you have your block, your payload, there are the green square, and then the blue, and the green square, and then the yellow square are the payload, and then you have your attestations, 4 seconds for that, and then you have your aggregated attestations at the 8-second mark, and then the net slot proposer basically does that, right? Okay, so next slide. So this is what's happening in reality today, right? Because of timing game, right? So let's just define some variables. You have your H second into the slot, the proposer gets header from the relayer, okay? So this is kind of like every validator implements different strategy. If you're a solo validator, you probably don't mess with this too much, but you're a sophisticated validator, you will try to fine-tune this H second parameter, which is very important, okay? And then say if you use MVV boost, you have R second into the slot. This is when the relayer releases the block, right? The relayer is kind of this trusted party in the middle. I'm sure everyone knows what the relayer does. The relayer verifies the block. The reason they verify the block is to prevent same slot unbundling attack. So R second into the slot, the relayer releases the block. Now, so nothing has changed from the attester's point of view, right? Just attester, we assume attester here is honest, that implements the spec. So at 4 seconds into the slot, the attester released their vote, okay? So now we fast forward to the next slot, 12 seconds later, it's the same thing, right? The H second plus the 12 seconds into the slot, the proposer gets a header from the relayer, right? So what is the reality here? The reality here is that like depends on how hard you push this H and this R variable, the attester directly has less than 1 second to verify the block, right? And then if today the block is released after the 4 second mark, then the next slot proposer will try to reorder it, okay? Today, I know for a fact that Prysm and Lighthouse has this implemented in a way that they will reorder a late block, okay? They can do it today because of this proposer boost, so they get 40% of the power, which I will go over slightly more what proposer boost does in the future slides, right? And then this behavior has like slightly worse implication because say, for example, the blob sidecars, right? The blob sidecars has propagation delay because there's more thing to be delivered on the slot basis. Say today you have very juicy MEV block, you want to delay until the very last second towards the 4 second mark. You may not want to include your blob sidecar anymore just because like, I don't want to risk this juicy MEV block where it gets delayed, right? So it's worth mentioning the timing game can like come from like proposer or relayer. Some of them have their MEV boost that's fork that implements timing game behavior. And then there is this R, which is the relayer verification time, because the relayer needs to verify that the proposer indeed signed the block, or signs the block, and then the block is validated. Otherwise, there's same slot unbundling attack, which we have seen last year, and that's really bad. So this is a timing constraint in Ethereum, right? Sorry, I misspelled timing. So everything happens in between R second to 4 second mark. So we call that the hot path, right? So what happens during those times? Because everyone is trying to rush and get everything done within that gap. Otherwise, the block will get reorged, right? So from the client's perspective, you're running a node, or if you're running a node on your local home, or like in the cloud or somewhere else, you will see this obvious. Your bandwidth, your CPU will spike, your memory will be fully utilized within that R second, the release second, and the 4 second, right? And why is that, right? Like what is the client doing during those time, right? And then I define 3 processes that can happen in parallel, okay? The first thing is that we have consensus state transition, and that is to verify the consensus state. That's to verify all the signatures from the attesters, to hash true the Bayesian state, and then anything that touches the current validator size will take a while, because we have 1 million validator. That's a lot of validator, right? And then on the other hand, you have execution state transition. This is what Geth does. This is what Ref and Nethermind does, right? They have to process the EVM. They have to update their execution state route, and that is also very expensive as well. And that's sort of the bottleneck today. And then you have to wait for all the blob sidecars to arrive before you do anything, because this is the data availability guarantee, okay? So after you've done those 3 things in parallel, if you see my diagram, you do consensus, you do execution, you do data availability, all those 3 happen in parallel, you run your 4-choice rule, you calculate your new head, and then you wait for that, you basically wait, and then basically you can vote, right? But if you miss that deadline at the 4 second mark, the node will vote for the previous head, and that's how reorg happens, okay? So so this is basically why it takes long, right? So ideally, if you wanna reduce the latency between this R second to the 4 second, this is where the bottleneck is. So what is the problem, right? Like if we have this like contention, right? Because you can think of, like, on one hand, we want the proposer to do as many stuff as possible, right? We want to increase the blob gas limit. We want to increase the, do some pre-confirmation stuff. We want the proposer to carry more duties, right? But then at the same time, the time is getting shorter and shorter because of there is timing and delay, right? So like the forces from 2 sides, they contradict with each other, right? So in a way, it's hard to raise the execution gas limit, assuming the state growth is no longer a concern because of this limitation, right? It's also hard to raise the blob and target match limit. We have to be careful with the inclusion this size. We also cannot decrease the slot time. I know Vitalik has been talking about decreasing the slot time to 4 seconds. Obviously, we cannot do that, right? Because of this risk, right? And there's also this centralization risk as well, right? Because now we promote co-locations, we promote vertical integrations, and this doesn't really work well with any other protocol services because we only have less than 1 second to verify the block, right? Such that like there's pre-confirmation, there's DVT, there's AVS, there's so many things people want proposals to do, but we cannot do it today, right? So here is what PBS solved that I am very excited about, okay? So all the PBS scheme, like block auction, slot auction, EA, ET, blah, 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 they all have this common pattern such that the consensus and the execution are pipelined under different phases, okay? So that is very cool. If you look at the diagram on the top, this is what we have currently, right? Your node is just sleeping, it's not doing anything. Then the 3 second comes, it goes this crazy spike out phase, then goes sleeping again for another 8 seconds, right? But then theoretically, wouldn't it be nice to like kind of even out the spike such that your node is just working all the time, like incrementally, versus just having a spike, right? So any PBS model that we have defined so far, that the consensus block is released in the first half of the slot, and then the execution block is released at the second half of the slot, right? And because of that, you kind of have these 2 mini slots together. So therefore, you have this pipeline approach, and then your node is not like it's not so like heavily strained within that 1 second, right? And it's even nice because your blob sidecar can be released earlier. Your inclusion list can also be released earlier as well. And then most importantly, your execution block no longer affects the consensus liveness, because say today, the builder failed to reveal the block or reveal an invalid block, then it just becomes an empty slot. But then the consensus information is still there, and that is very nice. So maybe like a brief intro on what is inside the PBS slot. Here I will use an example for block auction and also slot auction. So how it works today is that when the 0 second into the slot, the proposer releases the consensus version of the block. But this consensus block commits to the header, which is just-in-time block building. Basically, it's a blind block. You can think of that. Or it could just like commit to a builder ID. We don't need to commit to the actual content, right? You commit to the builder ID. And then 3 seconds into the slot, the attester releases their votes. And 6 seconds into the slot, the aggregator releases their aggregated vote. This is the same as today, but we moved the timing a little bit earlier. And then also 6 seconds into the slot, the builder here releases their payload or their withhold message, which I will explain a little bit what this withhold message is. And then the 9 seconds into the slot, you have this extra set of attester, which we call them payload attester, that release their votes on payload timeliness. So this is very important for any PBS scheme, that we need to introduce a second set of actors. For this, we call payload attesters. We need someone that's trusted in consensus to vote on whether the builder revealed the payload timelinessly. Otherwise, otherwise, like, there could be many attacks, right? So this is the main difference. And this payload attestation, this payload attester, theoretically basically just does what the relayer does today, right? But it is trusted on chain. Okay, so this is an interesting slide, right? So this is where the new time constraint in PBS. So remember before, we only have 1 second to do everything. We need to verify the consensus block. We need to verify the execution block. We need to verify the blob sidecar, right? But now we have more time. So right now, say assume there's still timing game, because that's inevitable in any scheme today. So the proposer releases a block as late as possible towards the 3 second mark, right? But we know from the pre-merge days, verifying consensus block is fast. Today, it takes about 100 milliseconds to verify a consensus block. It's mostly the execution block that's taking a really, really long time. So 1 second to verify the consensus block, and then you have 3 seconds to verify, to ensure the execution block is revealed on time, right? This is very interesting, because now we just need to, as a payload tester, we just need to verify it is revealed on time. We don't really care about execution validity until the next slot, which is something that we will learn just here. So at the 6 second, so now, let's see. Okay, so now as your next slot proposer, you have 6 seconds to verify the execution block, because you need to verify like what block you want to build on, right? So you don't want to build on the wrong block. You don't want to build on the wrong block, so you have 6 seconds to do that. And now you ask, like, who is going to verify the execution block, right? As it turns out that you can have 9 seconds to verify the execution block, because you only need to verify the execution block if you think that block is head, right? So that just gives you a lot more time. So now you have 9 seconds to verify the execution block as the next slot beacon attesters, right? And then as a builder, you have 6 seconds to build the block. And then because of there's no like same slot unbundling for blob sidecar, you can release a blob sidecar a bit earlier, even as you know, when the proposal include your header. So you can, if you release your blob sidecar earlier, assume you are altruistic, you have at least 9 to 12 seconds to verify the blob sidecar for data availability, okay? So now, see, this is a big mental shift, right? We go from before that we have 1 second to verify the execution block. Now you have 9 seconds to verify the execution block, and 9 to 12 seconds to verify that the blob sidecar's data availability. So what are the design challenges, right? I mean, everything comes with trade-off, right? This is not free, basically. So like, so the good thing is that the changes are consensus layer only. There's no execution layer change, so that's nice. But there is a great amount of for-choice there's great amount of for-choice complications because we go from like traditional like block voting to block slot voting to block slot payload voting, right? And then you basically, we have to ensure like there's a good safety margin for different actors, such as like proposer reorg, such as builder reorg safety. We also want to maintain the same like 12-second slot time. And because of that, we have to reduce the current run from attestation from 4 seconds to 3 seconds, and aggregation from 8 seconds to 6 seconds, right? And as a builder, you have 2 seconds less to build a block. So today you have 8 seconds to build a block. With this model, you have 6 seconds to build a block, right? And then we also have to make sure that the builder feels safe to reveal the block, right? The builder will only reveal the block if they know the block that's committed to its header is strong enough in the for choice. Otherwise, they don't want it to get reordered, right? So here I want to define 2 parameters. So I will go slightly faster because I have 5 minutes left, but feel free to ask me any questions on this after. So the builders will want to ensure 2 parameters. The first is reveal safety. The second is withheld safety, right? So those 2 are super important, so I will just say out loud, is that for the reveal safety, we want that if the builder acts honestly, and then if you reveal the payload on time, as seen by majority of the payload timeless committee, then the payload should stay on chain, okay? So here we're giving a reveal boost, meaning that if the builder reveal on time, this PTC committee voted on the payload, then this builder's payload that commit to the block will get 40% of the committee weight. So this is very important property to have. But we also want this withheld safety. So this is, again, very important, that if today the builder doesn't want to reveal the block, the builder can essentially send this withheld message, right? Here's one example why the builder will want to do that. It's because, say today, a proposer commits to the builder's header close to the 4-second mark, try to grief the builder, right? But the builder is not sure what you should do, right? Because the builder could reveal it, but if you reveal it, then that could get reorg, then the builder has to pay. But then if the builder doesn't reveal it, then the builder still has to pay, right? So we give this builder this option to essentially send this withholding message saying that I don't feel comfortable on revealing this, such that I would give weight to reorg the block, such that I would give weight to the parent block of this current block. So this allows builder to basically have a way out saying that, yes, I don't feel comfortable. So I will go very brief today on this type of attack. So today we have post-anti attack, we have ex-anti attack. So those 2 type of attack they're modeled in a way that say like I have a proposer n, I have a proposer n+1. The proposer n can reorder of the block of n+1, or the proposer of n+1 could reorder block of n. So today a lot of attacks are under 2 models. But on PBS, this gets significantly more complicated because now there's 3 players in the game, right? Remember, before we have 2 players, we have proposer n, proposer n+1. But now you have 3 players. You have proposer n, builder n, and proposer n+1. And such that any of those 2 players could team up and then attack one another, right? So you can imagine today, I'm a proposer n, but then the builder that I'm committing to team up with the proposer of the next slot and try to screw me over, right? Or you can think of some sort of sandwich attack. You have proposer n, you have proposer n+1, and then they try to mess with the builder in the middle by trying to reorder it out, right? So we have been yeah, so this is this type of game that we have been modeling. And then we have like a pretty good study of it right now. Most of our research are on ETH research posts. I probably shouldn't go over this like line by line because it's probably too dense right now. But I highly encourage people to visit our ETH research post. We have a pretty good model on post-NT and ex-NT attack. And then build a reorg and withhold attack, right? So here we're looking for feedback. Like we're looking for feedback from the searchers, the builders, the validators, the relayers. I mean, we just released our EIP, it's EIP 7732. This is the one that documents the block auction for EPBS. We also have a biweekly EPBS breakout call. Feel free to join. Ethereum R&D has a Discord channel. There's an EPBS channel. Feel free to ask your questions there or DM me on Twitter or Telegram. Yeah, I'm looking for feedback on any of these talking points, what makes sense and what doesn't make sense. So yeah, thank you for hearing my talk. And if we have time for questions or...
Thank you for the talk. How does this approach compare, at least like what's the major trade-off with delaying the state root calculation of one slot?
Yeah, so I know for a fact Paradigm, Red Team, has been doing a lot of study because they have this vision, they want to do 1 gate gas limit, right? And there's no way you can do that today, assuming the state growth problem is solved, right? So they have been thinking alongside some sort of delay state root approach, right? And this is solve exactly the problem. And this is why we realized that actually a month ago, we didn't even realize we could do that. Because when we think about EPBS, we just think about like solving MEV problem, like centralization problem, and then getting rid of trust. But it turns out EPBS has this very nice property that you can do delay state root validation. Because for execution state, you don't have to verify it until the next slot, such that you get 9 more seconds. And this is exactly that. Yeah.
Thank you.
I will also be around after, so yeah, feel free to ask me anything. Okay.
Awesome.
Thank you.